So hello everyone, I'll talk about forecasting constraints on non-thermal LiMRs from future CMB experiments, and this topic will be based on this work which I did with my supervisor Anshuman Maharana, Orko Banerjee, Shubhinoy Das and Ravi Kumar Sharma. This is a plan for my talk. First I'll give some introduction and motivation for our model, and then talk about for our work, and then I'll talk about our model, and then discuss about feature analysis, and talk about my results and discussions. And then I will talk about higher limits of the distribution function. What this is will become clear when I move into the talk. And finally, I will conclude my talk. So the total radiation energy density in the universe post neutrino decoupling, or more specifically after electron positron annihilation, is given by this expression. Here N effective is called the effective number of neutrino species, but as you will see that it can have contributions from extra relativistic particles which have nothing to do with neutrinos. The standard model prediction for N effective is 3.044, but from DCO to CMB measurements, we get this value at 68% confidence level. And this indicates that there is room for non-zero delta N effective. And future experiments will probe delta N effective with even greater precision. Generic feature of many beyond standard model proposals is the presence of new light relics which behave as dark radiation and contribute to N effective. Sterile neutrinos which have been proposed to address anomalies in neutrino oscillation experiments are a candidate, but a fully thermalized forced sterile neutrino which follows the Fermi-Dirac distribution that is not allowed. But a hot thermal relics which decouple from the thermal plasma prior to neutrino decoupling, they are allowed, and their contributions to delta effective are given here if you assume that they decouple prior to at a temperature greater than the mass of the top quark. And for massless relics, the cosmological impact is completely captured by this delta effective parameter, and Benjamin Walish with Daniel Bauman and others have worked on this. The other possibility is that of light massive relics, massive particles which contributed to the radiation energy density in the early universe and to the matter density at late times. And future forecasts from future experiments for thermally distributed scalar vector Ryle Fermi Dirac Fermi relics have been performed by Linda Zhu and Deepo Zhu and others. Now, the influence of light massive relics on linear cosmological observables can be characterized by three parameters. Delta N effective, this represents the contribution of the LiMRs to the relativistic energy density of the universe prior to recombination, and MSP effective represents the contribution of the LiMRs to the total energy density today, and if this is the free streaming velocity of the LiMRs. From here we see that of the three, only two are independent, and for our work we consider delta N effective and MSP effective as the phenomenological parameters to investigate their impact on linear cosmological observables. Now coming to our model. So we consider the decay of the inflaton or moduli mostly to the standard model sector and partly to the dark sector, which leads to a transition from an early matter-dominated era to radiation-dominated era in the early universe. And due to interactions, the standard model sector that is fully thermalized, but the sterile sector is not thermalized. And we consider the decay to the sterile sector to be of this 1 to 2 decay with a branching ratio BSP. The late time distribution functions of the non-thermally distributed sterile particles LiMRs was found in this paper by Sukanya Bhattacharya, and this is of this form. E hat is the energy of the sterile particle sap production, N0 is the initial number density of the inflaton of the modulus, this was a branching ratio to the sterile particles like I mentioned. SR, this is just the scale factor as a function of theta, which is a dimensionless time parameter defined as T over tau, tau being the lifetime of phi. And H is the dimensionless Hubble parameter. Y is defined in this way. Here theta star indicates that by this time all the phi is assumed to have decayed, and Q is the momentum in units of the typical momentum of LiMR today, and this quantity N0 can be expressed in terms of the CMB temperature. Our model has four macroscopic parameters. One is BSP, that is MSP, and M phi, which is the mass of the inflatonal modulus, which we take to be of the order of 10 to the power minus 6 Planck mass, and tau we take to be of the order of 10 to the power 8 over M phi. The phenomenological parameters have these expressions. Here MSP is the physical mass of the sterile particle. And we also compare the results with a simple distribution function, the Radisson distribution function. So non-resonant active 12 neutron oscillations in the early universe in the limit of small mixing angle gives rise to this expression for this 12 neutrinos, this momentum distribution function, which is just a rescaled Fermi-Dirac distribution. And in the limit of instantaneous neutrino decoupling, the phenomenological parameters take these forms. This shows a comparative plot of the inflaton decay model distribution, which I denote as NT non-thermal, and the DW distribution. And this has been plotted for same values of the phenomenological parameters. For this plot, we chose delta effective to be 0.034 and MSP effective to be 0.903 electron volt. And the corresponding model parameters are shown here. This is for the non-thermal model and this is for the Robinson-Vitrone model. So a reminder of the basics of Fisher analysis. So the idea is that if we have a set of data and a model and with a set of parameters, we can readily compute the probability of x given theta. But how do you compute the probability of theta given x? Base theorem raised these two. This p theta x is called the posterior, this p theta is called the prior, this is called the evidence. And px theta, this is called the likelihood, which is defined as the probability that an experiment yields the observed data given a theory. And in the limit of large amount of data, the likelihood can be expressed in this Gaussian form. Here C is the data covariance matrix and X is the data vector of dimension n. The Fisher matrix is formally defined as the curvature of the log likelihood function related at the fiducial values of the parameters. And this quantifies the amount of information that a given experiment can provide about a set of parameters. So it's called forecasting. So it shows if the curvature is high, then the constraints will be tighter. And if the curvature is low, the constraints will be wider and the error will be greater. The error estimate, the error covariance matrix is defined as the inverse of the Fisher information matrix, and the margin is 1 sigma uncertainty of the parameters is given by this credit of the diagonal elements of the covariance matrix. The non-diagonal elements determine the shape and size of the red ellipse in the parameter plane. Now for CMB experiments, the Fisher matrix takes this form. The tail plus 1 is the number of modes per L. Let's get the fractional sky coverage for the experiment. Here is the spectral covariance matrix, which is shown here. And this includes the Gaussian noise for temperature and polarization. Here plus with instrumental noise in temperature polarization and theta division is the resolution of the experiment. And NR55 is obtained from minimum various combination of various quantitative. So the fiducial model for analysis consists of these 6 lambda Cilium parameters and these 2 phenomenological parameters. We consider 2 sets of fiducial values. The first one corresponds to the best fit of MCMC with Planck 18 and SA data sets performed in this paper for the model. And set 2 corresponds to the values of the 6 lambda Cilium parameters from the Planck 18 paper for the lambda Cilium model extended by delta effective and MSP effective. And like for set 1, in set 2, the Planck method we used this prior on the mass of a thermal foil particle, which leads to these bonds on delta effective and MSP effective. And this quantity is related to a phenomenological parameter MSP effective by this rate. So this shows a comparison of the residuals of T10 and 5 spectra. Increasing delta effective just leads to more damping of the CMB tail as expected, and even though for step 2 the mass is lesser, so the free stream velocity is greater, but the suppression is less. This is because in step 1 a greater part of CDM is replaced by LiMRs, and so it has less stress strain component and hence more suppression. This shows the experimental parameters which are used for a plan and a particular program the CMB stage for experiment. This one is in microkelvin arc minute and this is in arc minute. And we just read the exhaustively joint analysis of Planck and CMB S4. We added these two Fisher matrices to ensure that we don't develop in the region of overlap. We get these results for the phenomenological parameters. First thing we notice is that for both the non-thermal reducing with models. We get similar constraints on delta effective and MS effective, and this is true for both sets. This shows the Fisher plots for these parameters, omega is omega b plus omega c. But sorry. Okay, but for set 1, the return related MS2 is slightly degraded as compared to set 2. Delta effective and MS effective are positively correlated for set 2, but they are negatively correlated for set 1. And delta effective and H are negatively correlated for both sets, which is unlike in the case of standard neutrinos where they are positively correlated. This shows the evolution of the LiMR energy density. Set 1 corresponds to the heavier LiMR, which contributes lesser to the radiation energy density due to its lower abundance, but comparatively greater to the matter density compared to set 2. This shows the evolution of decrease of state parameter for the LiMR. The blue curve, it corresponds to set 1. We see that this heavier particle becomes non-relativistic just before matter radiation equality, and at the time of recombination, it contributes totally to the matter density. And for set 2, on the other hand, we see that it has still some non-zero contribution to the relativistic energy density, and as such, the heavier LiMR, it becomes sensitive to CMB almost exclusively through its effect on the weak length signal. Sorry. So in your paper, we have used these and tried to explain our results. So we saw that when we matched the first two moments, which are related to the two phenomenological parameters, we obtained similar results for the non-thermal and Rhodolphin distribution. And to include the effect of a higher moment, we considered an Edgeworth-like expansion about Rhodolphin video distribution. For PEM, these are orthogonal polynomials which are orthonormal with respect to a measure q square over e to the power q plus 1. This we can write simply as alpha plus beta q plus gamma q square. And when you match the first two moments of f and fdw, then we can write alpha and beta in terms of gamma. And f, which earlier had one parameter chi, now has two, chi and gamma, with the requirement that the meaningful distribution function has to be non-negative, restricts the range of gamma to this. And gamma equal to 0 corresponds to Rhodolphin video distribution. Here I have plotted the modified distribution with matching first two moments, but the third moment refers to the maximum possible extent. Again, we perform Fisher analysis with the 6 lambda CDM parameters and delta n effective, MS effective, and gamma. And this figure shows the results. And we see that a significant overlap between the posterior distributions for the two models with gamma equal to 0 and gamma equal to 0.25 indicate that any CMB S4 like experiment is unlikely to distinguish between these models. However, from our results for a hypothetical cosmic variance limited experiment, it indicates that a future experiment with better sensitivity can potentially distinguish between these two. Now I will conclude. So you see that the constraints on delta n effective as well as delta n effective and MS effective degeneracy directions depend on the time of non-relativistic transition. For a heavier LiMR, which becomes non-relativistic well before recombination, delta n effective is more tightly constrained. And that is owing to the fact that changes in omega and omega sp at recombination cannot be replicated by changes in delta n effective. We obtain similar constraints for two different models with visibly different distribution functions once delta n effective and MS effective are matched. Furthermore, two models with matching first two moments, even with maximally varying higher moments, cannot be told apart by CMB S4 like experiments. And combining CMB experiments, galaxy surveys like LSST and Euclid, as has been done by Depozo and collaborators, and going into the nonlinear matter power spectrum, can create degeneracies and yield signatures tied to the LiMR production mechanisms, which our linear analysis is inherently insensitive to. We use these packages class or fix and fish chips. And with this, I'll end my talk. Thank you.
Thank you, Abhi. Time for a question or two.
So I have a very naive question. So because these LiMRs, they act as relativistic particles in the early universe and become massive later. So how will your results change if you include the DZ data? Because it kind of, it says that omega n is lesser than expected. So, I mean, how would your results change if you included easy data?
Okay, I don't think I'll be able to tell that if include this data. I don't know, I have to see.
Okay, thanks a lot.
Ranjan.
Hi, thanks for the nice talk. I have probably a more model-dependent question. So
Correct.
you're producing these non-thermal light massive relics from inflaton decay.
Yes.
So is there any relation so since presumably inflaton also produces the standard model particles, is there any relation between these particles or coupling between these particles and the standard?
No, we are not considering any coupling. We say that the inflaton decays mostly to the standard model sector and partly to the dark sector with a small branching ratio, and there is no interaction between these two, between the dark sector and the standard model sector.
Okay, thank you.